Question 3. So we consider this matrix. This is the matrix. Show that as n tends to infinity, p to the power of n x0 approaches 0, 1 for any vector ab, and the sum of ab is equal to 1, ab positive numbers. Okay, so for this question, as long as we know what is my p to the power of n, okay, we should be able to take the limit of this whole thing and see whether it approaches 0 and 1 or not, right? But the problem is how to get this p to the power of n. It might be very difficult if you try to multiply it one by one and see patterns, and it might not work, right? So what can we do? We can make use of the result from the previous question. It says that if p is diagonalizable, then this is just what diagonalizable means. We can find m such that m inverse pm is equal to d, okay, where d is a diagonal matrix. And if p is diagonalizable, we can also use the same m and d, and p to the power of n is just m d to the power of n, m inverse for any n. Okay, we will make use of this, but then what we still don't know is whether it is diagonalizable or not. Okay, so proof. So what we have here, p is this, so we have consider 0 equals to the determinant of lambda I minus a. Sorry, in this case it is p. This is to find the eigenvalues for p. This is equal to lambda minus 0.5, 0 minus 0.5, lambda minus 1. Okay, and clearly the determinant of this is just the multiplication of this and this, right? So this means we have two eigenvalues, which is 0.5, 1. Okay, next we need to find the eigenvector for this eigenvalue and eigenvector for this eigenvalue. So let's do it one by one. So for lambda is equal to 0.5, we want to find x not 0 such that 0.5i minus p multiplied by x is equal to 0. In other words, it's just 0, 0 minus 0.5 minus 0.5. x1, x2 is equal to 0, 0. But this is just minus 0.5 x1 minus 0.5 x2 is equal to 0. Okay. Imagine if I let this x2 to be a free parameter, I can express x1 in terms of that free parameter. So let's do that. So let's say if I let my x2 to be t, which is a free parameter, then my x1 is just minus t, right? Because from here, I use red color, you know that x1 plus x2 is equal to 0, means x1 is equal to minus of x2. Hence, we have found our x, which is t minus 1, 1. T is real number. So we can take this as our eigenvector for lambda equals to 0.5. Next, for lambda equals to 1, same thing. We want to find x that is not 0, such that I minus p is equal to, minus px is equal to 0. In other words, it is 0.50 minus 0.50, x1, x2 is equal to 0, 0. Okay. This gives us 0.5, 0.5 x1 is equal to 0, and minus 0.5 x1 is equal to 0. Both of these imply x1 is equal to 0, and there is no restriction on our x2, so we can let x2 to be free parameter, but my x1 must be 0. So my x is just in the form of t times 0, 1. T is a real number, and we can pick this as our eigenvector for this lambda. Okay, and clearly the set containing these two vector is linearly independent. So clearly minus 1, 1, comma 0, 1 is linearly independent, right? So this p, hence p, is diagonalizable. Okay, very good. So this p is actually diagonalizable. Okay, so we can find m that satisfies this. Okay, hence let m to be minus 1, 1, 0, 1. Okay, then I will have m inverse pm is equal to d, right? M inverse pm is equal to d, and d is just a diagonal matrix with this entry is the eigenvalue for this, and it is 0.5. Also for this, it is 1. Okay, let's call this d. Okay, and from question 2, we know that for any n, for any integer positive integer, okay, for any positive integer n, we have this p to the power of n is equal to m d to the power of n m inverse. Okay, so since m inverse, how to find the inverse of this? 1 over the determinant of this, which is minus 1. Okay, then swap this, minus minus. So I will have minus 1, 0, 1, 1. Right. Then p to the power of n is just m is here, minus 1, 1, 0, 1 times d 0.5 power of n, which is 0.5 power n. 0, 0, 1 power of n is just 1. And this is minus 1, 1, 0, 1. Let's compute this. We have this is equal to minus 0.5 power of n, 0, and 0.5 power of n, and 1, multiplied by minus 1, 0, 1, 1. Okay, I obtain this from multiplying these two. After this, what can we do? Multiply again. We'll have this multiplied by, I will get minus 0.5 power of n, then this is 0, and this multiplied by this, I will get 1 minus 0.5 power of n, and this I will get 1. Okay. Okay, good. Then, okay, we can find p to the power of n multiplied by x0, and this is simply 0.5 power of n, 0, 1 minus 0.5 power of n, 1, multiply with ab. This is equal to what? Minus, shouldn't be minus. Oh, okay, I made a mistake here. This is positive. Yes, okay, this is positive. Just now, why this cannot be minus? Because, okay, never mind. So I will have a times 0.5 power of n multiplied with a 1 minus 0.5 power of n, which the power of n is here, plus b. Right, so I will have a 0.5 power of n, and here is a plus b minus 0.5 power of n. Good. And we see that as n tends to infinity, this will tend to 0, and this, I miss a here, a times, that's right, a times 0.5 power of n, and this will also tend to 0, right? So as n tends to infinity, p to the power of n x0 tends to 0, a plus b, but a plus b is 1. So as n tends to infinity, this will tend to 0, 1. Okay, done. Okay, hope it is clear. It is quite long. Okay, but as long as if you know this, okay, if P is diagonalizable, then shouldn't be too difficult. Okay, hope it is clear.